Let's talk about probability distribution. I might ask people, how many eggs did you have for breakfast this morning? And usually probably the number will look like this. X equals the number of eggs you had for breakfast. Now I didn't say fried eggs, poached, whatever, hard boiled, but how many eggs did you have for breakfast? 0, 2, 7, 7, 1, 8. Could some of you have 0 eggs? I didn't have any eggs this morning, so I had 0 eggs for breakfast. It's possible. 1 egg, 2, 3, 4. Anyone had more than 4 eggs today? Hope not. Your cholesterol will be too high. But usually 5 and 6, whatever, you know. So you list actually the number of eggs, and on this side you list what we call the probability. So that's why this is called probability distribution table. So the probability distribution table gives the probability of each value. That's what it does. It gives the probability of each value of x.
Move it over to the left a little bit.
More?
Yep. That's good, that's good.
So it gives the probability of each value. I can't shrink it now. I can lower it a little bit there. So here I can write some numbers, and there's no way to verify if I'm really right or wrong. 0.05, 0.20, 0.25, 0.15, 0.15, 0.10, and 0.05. And let's do 7 eggs, 0.05. Somebody likes really eggs. Let's say that's our table. That's known as probability distribution table. It gives you the number of eggs a person can have and the chance, the probability of that happening. Now, if you're given a table like this, and the question is, does that look like a valid table? Now, x is the random variable that represents the number of eggs, and piece of x is the probability. But does that look like a random? Does that look like a valid probability distribution table? Well, a couple of things to look at the table and see if that's a valid probability distribution table, and that is the probability of any event always between 0 and 1. So look at each one of these numbers. Are they between 0 and 1? Yes. That's the first test. The second test, the sum of these, if you add all the probability, the sum should be 1. If I add all these numbers, if I did this correctly, I try to make it correct there, they should add up to a 1. 0.05, 25, 50, 65, 80, 90, yep, that's 1.0. So that passes that test. That doesn't tell me that people lied to us. There's no way to validate if people lied to us. What do I mean by that? Because somebody could say, you know what, I'm going to change these numbers. I'm going to make this number, instead of 0.25, 0.20, and make that number 0.10. That still fits these criteria. So it could be the wrong table. There's no way for me to see if that table is really correct or not, accurate or not. But I can tell you, based on these probability and the sum of them, if this looks like a valid probability distribution table. I didn't say correct or honest. I said a valid table. Because the probability of each event is between 0 and 1, and when you add them all, the sum is always a 1. Now, these events are known as discrete. Why discrete? Because their values is counting values. 1, 2, 3, 4, 5, or whole numbers, 0, 1, 2, 3. If we ask you how many glasses of milk did you have today, that's not really discrete. Could you have half a glass of milk? A third of a glass of milk? A teaspoon of milk in your coffee? So that number is not just 1 cup, 2 cups, 3 cups, 4 cups. That's called continuous. But this one is discrete random variable. X is a discrete random variable. Discrete has counting values, where continuous could have a decimal values. Now, if you're given a table like this, can you look at that table and tell us what the average is and what the standard deviation is? Let's take these numbers. Now I regret having a table that big there, but I'll put it there on the next page. I'll repeat these numbers. Again, X is the number of eggs, and P is the probability.
You don't want to move it to the side a little bit. There you go.
For 0, I use 0.05. I'll take the first table. For 1, I used 0.2. For 2, we had 0.25. For 3, 0.15. For 4 is 0.15. 5 is 0.10. 6 is 0.05. And 7 is 0.05. In my job here, I need to figure out what the mean is. What is that equal to? And what is the variance? We'll say sigma or s squared. I didn't tell you if it's population or sample. That's why it could be either one. And the standard deviation. Again, I didn't tell you if it's population or sample. So that's why I'm putting both letters there. I don't even know myself. So this one I should say the mean, which is x bar or mu. Because I never told you we tested a sample or population. Let's assume these are sample, because there's no way to ask every single person, how many eggs did you have today? Impossible. Unless I'm only interested in this class. Maybe somebody came to me and said, you know what, your class eats a lot of eggs. And I go, really, my class? He goes, yep. Let me ask everyone today. Well, even if I did, we're missing some people. That's still a sample. Maybe they're still eating the eggs in the cafeteria. Who knows? So how do we find the mean? When you are given probability distribution table, we can't use the equation we used before. Before it used to be the sum of x divided by n. Doesn't work here. If you have your handout that I posted on Blackboard, you will notice in it the mean, mu or x bar, whatever you want to call it, can be found by taking the summation of x times piece of x.
You move it over a little bit so you can just see that.
Joe, you're picky today.
Oh yeah, I couldn't see that.
Get out of here. Come on. The standard deviation is the square root of the summation of x squared times piece of x this is like this way. You add them minus mu squared. Those are the equations we're going to be using. So Joe can see them. Here we go. At average is the summation of x squared. At average is the sum of x times piece of x. And the standard deviation is the sum of x squared times piece of x minus mu squared. We take the square root of that. So I need to actually make a column here. And I want to make a column x times piece of x. And if I multiply them and add them, that's my mean. 0 times 0.05, 0. 1 times 0.20, 0.20. 2 times 0.20, 50. 3 times 0.15, 45. 4 times 0.15, 60. 5 times 0.10, 50. 6 times 0.05, 30. 7 times 0.05, 35. Let's add them. 5 and 5, 10, 0 carry 1, 3, 8, 12, 18, 23, 25, 28. So guess what they mean? Based on this sample, the average person in my class is the summation of x times piece of x. The average person eats 2.8 eggs per day. How do we get the standard deviation? Well, I need another column now for the standard deviation. That column is going to be x squared times piece of x. Now, I know you're all smart in math. So what will happen if we multiply these two columns? What is x times x px? Doesn't that give you that column? You can also square these and multiply them by that. But since you have these two, if you multiply them, x times x, x squared times the px, so 0 times 0 is 0. 1 times 0.2 is 0.20. 2 times 0.5 is 1.0. 3 times 0.45, what's that, 1.35? 4 times 0.6, 2.40. 5 times 0.5, 2.50. 6 times 0.3, 1.8. And 7 times 0.35, 3 times 5, 15. 5 carry 1, 7 times 21. Is that 2.25? Was it? 4 or 5? Thank you. 2.45. And now let's add them. 5 and 5, 10, 0 carry 1, 3, 6, 10, 15, 23, 27. 2 and 1 is 3, 4, 6, 8, 10, 11. 11.70. So I'll come back to this equation. What is my standard deviation? It's going to be 11.70 squared minus 2.8 squared, 2.80 squared. And where'd you go, calculator? Put it away, I guess.
I think the x times p of x column is 2.90. Yeah.
2.90? Is it? Could be. So that becomes 2.9 then here, right? Thank goodness for whiteout. That's a 2.90, not 80. I tend to believe you more than me. 11.7. There's no square here. I don't know why I said square. There is no square. The equation does not say square on it, right?
No.
Only the second one is square. I don't know why I wrote square there. 11.70, no square, minus 2.9 squared. So I'm end up with the result of what? 3.29. Take the square root of 3.29. It's 1.81 eggs. That's what the standard deviation is. So my variance 3.29. and my standard deviation is 1.81. The mean, the variance, and the standard deviation. Now the other thing is, while I'm at it, this section just slow, basic stuff. You'll hear the word expected value. The expected value, it's really nothing more than the mean. So the expected value, since the same as the mean, it is the summation of x times the probability of x. Now, I'll give an example for the expected value in a minute there. Just a reminder there why we're interested in the expected value, which is the mean, and the standard deviation, which is why we care about these. Because we can actually find what we call the usual value, the range from where to where for the usual value. Remember, the maximum, minimum, usual value are what? This is the standard deviation. This will be this is expected, the average, not the standard deviation. This point will be the average. What is the maximum, minimum value determined by what? Isn't that twice the standard deviation? And this is what? Twice the standard deviation. So this is the minimum usual values. Everything is designed based on these numbers. Maximum usual values. When we design something, we have to satisfy that group. The minimum group is that group. You got to make sure, for example, if you're flying this weekend, if you go on spring break, the seats on the plane, if you think it's by accident they made them that wide, you're nuts. They are designed to be that because that will cover 95% of the passenger. Actually, will cover more than 95. But we have to design everything that will fit at least 95% of the passenger. Now, remember, between these two numbers are what? 95% within two standard deviation. That's 95% of the people. That means 2.5% on this end and 2.5% on that end. So when we design the seats on the plane, if the seats are this big, these skinny people, assume these are the skinny people, they're going to have no problem sitting there. So the only ones really going to struggle is what? The 2.5% of the people. That's it. Because the seats are designed to hold 95%. And if you try to sue the airline, you're not going to win. The doors are 80 inches high. Why? That will satisfy the 90% of the people. The 95%. These two numbers. Actually, more than that, it will be 97.5 because the short people can still walk through the door if it's 80 inches or 84 or 76. But the tall people will struggle with that. So if we got the Celtics players coming in to visit us today, we're going to have a problem. Some of them will have to duck to walk through that door. But everything is based on these numbers. So that's why we keep going back to the mean, the standard deviation, why we're interested in that. Every design we do, is based on these numbers. We got to make sure it satisfies these two values. If you make it only one standard deviation, you open yourself for a lawsuit. That's discrimination. They made the door short. Every time I walk through, I bang my head. You make it that height, try to sue them, good luck. They go, hey, they're satisfying 97% of the people. We can never satisfy 100% of the people unless you make the door 10 feet tall. So you're not going to win. So everything is based on these numbers. This is the maximum usual value. That's the minimum usual value. That's why we go for that. Everything has to be within 2 standard deviation. That's the range. That's the rule of thumb that we use. Now let me talk about the expected value and show you where we use that. Now, if an event happens once in a blue moon, why do they call it once in a blue moon? The phrase blue moon.
Blue moons don't happen very often.
Nope. Just like blue lobsters. Anyone ever? It used to be the stat book says a blue lobster on them.
That's like 1 in a billion chance
Yep.
of a lobster or something like that.
The chance of getting a blue lobster out of that ocean is like close to 1 out of a billion. So it's not a frequent event. So once in a blue moon, if you research that on Google, how often a blue moon happens, you'll see one every, God knows, 40, 50, 60 years. Maybe in your lifetime you might see it once. So it's not often. That's a rare event. If something happens really once in a blue moon or once every 10 years, that's a rare event. If it happens every 10 days, well, that's not rare. Now, let's talk about the expected value. I meant to bring it back there and show you where we use that. The expected value of x, we said, is the summation of x times piece of x. One of the places we use that is insurance policies. Life insurance. When you buy a life insurance policy. Let's take Mass Mutual down the road from us. If you're not familiar with it, it's actually one of the top 100 companies in the U.S., Fortune 100. You can research that. They just had that a few years back, a couple of years ago. Their CEO does extremely well. You probably see his helicopter brings him in every morning. Have you ever seen that helicopter? Every morning. He goes to Mass Mutual about 7:40, drops him in. At 4:30, you see the helicopter comes and picks him up. He lives by Amherst, somewhere there. His salary is with incentive about $7.5 million a year. So it's not a small company. They sell life insurance. Well, they have to come up, when they do the math, they have to come up with a policy. How much should we sell a life insurance policy? Well, it's based on how much money they want to make. So for example, let's say I want to buy a life insurance policy on Joe. I said, there's a lot of people want to kill Joe. Let me buy a policy on him.
You can see that.
Yep. So Joe, I'm going to be a nice guy. I'm going to buy a $100,000 life insurance policy on you. Joe, are you 21 yet?
No, I'll be 21.
So he's young. So Joe's chance of dying of natural cause, because they don't pay you if you commit suicide or, other issues there. But to die just natural cause there, his chance is very slim. The probability of somebody his age group, not Joe in particular, anyone 20 and under to die is probably 1 out of, I don't know, I have no idea. Let's say 1 out of 5,000. I don't know. I'm just making that number up. One out of 5,000. So I go to Mass Mutual. I say, I'd like to buy a policy on Joe. He's 20. He doesn't smoke. He's healthy. He looks fine. Nothing wrong with him. They go, okay, that will run you. The cost for that is $150 per year. I'll take it. So what is the expected value for Mass Mutual? Expected value, I'm talking about Mass Mutual. You can use that logic for casino too. Mass Mutual looks at it. They're gonna look at it, win or lose. That sounds horrible, win or lose. How much they win if they win? Well, they win if what? I'm talking about Mass Mutual. They win if nothing happens to Joe. And how much do they win?
100,000 plus 150 per year.
Nope, they won. They didn't win the 100,000.
Well, they kept the 100,000.
Yeah, but that's not winning.
They win the 150.
They won $150. If something happens to Joe, I hope nothing happens to you, Joe, I don't want to kill you.
Thanks.
They lose. They have to give us 100,000. So what did they lose? They didn't lose 100,000 really. They lost what? 850 is it? 99,850 bucks. Because you already gave them 150 bucks. Let's find the probability of each event here. So what is the probability of Joe will live? Because remember, win means Joe lived. To live, that's what? If the chance of dying 1 out of 5,000, the chance of living is what? 4,999 over 5,000. And the chance he will die, will lose their money is 1 out of what? 5,000? We can convert these numbers now to percent if you want to. Let me find x times piece of x. Why? Because if I add them, that's my expected value, which is the average. The average is the expected value. So let me go to my calculator and see if we're going to make money, or Mass Mutual is going to make money on that policy. 150 times 4,999 divided by 5,000. That number is positive 149.97. Let's look at the negative value. Negative 99850 divided by the 5,000. That number is negative 19.97. So what's this number? 130. So what is the expected value for Mass Mutual? It's positive 130 bucks. What does that mean? Based on these numbers, Mass Mutual will make $130 on every policy we sell to somebody like Joe. That's what they expect to make. 130 bucks. Now, we could reverse the problem. I could say, you know what? We are running a non-profit organization. I'm working for the Knights of Columbus. And the we're not trying to get rich off this, Knight of Columbus. We just want to make sure we don't lose money. Can you tell me what price should I sell the policy for, the same policy, knowing these numbers? What price should I sell them if I want my profit to be only 30 bucks? I just want to pay my cost, my paperwork, and my guy to come into your house and get the policy. So what price should I sell them? So again, the story is not changing. We're going to buy again for Joe, 100,000 policy. The chance he will die, still 1 out of 5,000. And the cost is unknown. But I want the expected value of X to be plus 30 bucks. I only want to make $30 per policy, so I can, when I print the papers and buy the ink cartridge and send the people to your house to get the policy, we pay for the fuel, we pay for the 1 hour with you and the paperwork. So can you tell me what the price of that policy should be? We work the problem reverse now. We go win, loss, we're not sure we're going to sell them for. Let's call it X. That's the price, right? The amount. I have no idea how much I'm going to charge. So, and there's the probability of that. the probability will be what? 499 over 5,000. The loss will be what? If something happens to Joe and they have to pay us the money, they gotta lose how much? 100,000 minus X, right? That's what they're gonna lose. 100,000 minus X. And the chance of that happening 1 over 5,000. Remember, I want this number to be 30. I'm working it backward now.
Shouldn't that be 4999?
4, 9, yeah, one more 9. Trying to kill you there, Joe, I told you. Yep. So now X times piece of X here. This will be 4999 over 5,000X. If you do the math, isn't that X minus that number? Mathematically?
Yeah.
That's really X minus 100,000, because it's a minus there in the front, over what? 5,000. The minus sign is going to make that a minus, make that a plus. When you add these two numbers, should equal to what? 30 bucks. Let's do the math here. X over 5,000 with this, that'll give me 1x. Minus 100,000 divided by 5,000. 100 by 5 is 20. Equals what? 30. Take the minus there. The policy should be how much? 50 bucks. If we sell the policy for 50 bucks instead of 150, we can have expected value of 30 bucks, and that will cover our cost, and I'm okay, and we're not trying to make money off that deal. If you like this type of work, if you're a math major, that's what actuarians do. When Mass Mutual trying to figure out what is the price of a policy we should have, they look at the numbers, what's the expected value, and they calculate that based on this. They have a goal in mind, how much money they want to make, and they work the problem backward, and they figure that number. Actuarian make about 100,000 a year. It's a good job, actually. You're grinding numbers all day long for them, you know. But that's what they do. Couple of things just to remember from this section before I move forward. This is the expected value. Unusually high and unusually low. When somebody is unusually high, you know, you go, well, that's really high. I'll go like this, high / low. That means the probability of that event is very small. It's usually less than or equal to 0.05. If the chance of something happening is less than 0.05, we got unusually high, unusually low. Meaning what? If you're on that end of it here, and this number here, we got a number for you. Let's say this is the quiz average. We did a quiz average. We say, oh, boy, everyone actually was in this number and higher. That's unusually high. If that value is 0.05, that's unusually high. If everyone in this graph, or if everyone bombs the test on this end, physics test, that's unusually low score. Everyone failed it, you know? Everyone on that end. So if you're on this end, that's unusually high. If you're on that end, that's unusually low. If the percent here is below 5% on this end, that's unusually low. If the people above you, within 5%, above you in the top 5%, that's really unusually high. So you'll hear that unusually high and unusually low. So unusually high is 5% of the people have, you in the top 5%, X to be here or more. So I like to be unusually high, the way I would write that. That the probability of X or more, to get that number or more, let's say this is X, to be that value or higher, if the chance of that happening is less than 0.05, that's unusually high. Unusually low, the probability of X or fewer, less than that, is less than or equal to 0.05. That's in this group. This is unusually low, that's unusually high. So if your chance of happening, getting that number or higher is 5%, that's unusually high. I just got the letter, it says the acceptance rate at Yale, and, because, my daughter goes to Yale, so I don't have to tell you that, but we get these newspapers saying, last year was 6.8%. So they only accepted, this is the acceptance, they rejected all these people. Only the top 6.8% of the applicants actually got into Yale. The one who applied, not the students, the one who applied to Yale. I forgot that, 23 applicants, and they took like 1,000 people or 1,500 people. So 6.8%, that's unusually low, like unusually high, usually even lower than that. So that number only, if you're in this group, you go into Yale. So people who accepted to Yale is actually fit the criteria higher than this score or higher, that's unusually high there. Yeah. Rejected, all these people got rejected. Same thing with Harvard. Harvard probably has lower rate than even Yale. And that's the end of section 5.2. The next topic, which is binomial distribution, that's where the fun begins, but we'll talk about that after the break.